All right, now we get into bonding. Finally, after 10 weeks, we get to bond. Okay, so we've done a little bit, I think, in chapter 2. Okay, when I mentioned a few things to you, because it does make our life a lot easier if we understand bonding before we do nomenclature. But rest of it we're going to do now. So, and I'm going to review with you really quick. Okay, and I know you will remember a lot of this. So we have ionic bonding and we have covalent. Ionic is sharing or transfer? Transfer of electrons, and so covalent must be then sharing of electrons. Okay. Ionic is between metals and metals, or metals and non-metals? Metals, non-metals. Covalent is just between non-metals. All right, and one thing more about ionic that's not in covalent, and that's only because of the transfer of electrons, is you form ions, of course, okay, because it's ionic, so you form ions, and the two ions that you have are cations and anions. So none of that has changed, okay, so far. The cations are still positive, anions are still negative, cations are still formed from giving electrons, anions are formed from taking electrons, okay, and so you get the charge respect to whatever electrons have been given or taken. I need to remind you, okay, that bonding is an electronic property, okay, which means it has nothing to do with the nucleus. The protons and neutrons are intact, and that's how we get the charge, okay, because in case of cations, electrons are given away, which means you have more of the protons, okay, so more positive versus negative. In case of anions, the atoms accept electrons, so if they accept electrons, then they become more negative, okay? All right, so generally you have the +1, +2, +3 for group 1 to 3, and then ±4 for carbon group, and then -3 to 1, okay, from then on. So those things are still valid, okay? All right, so when we get to bonding, I'll do the ionic first, okay, because ionic is a lot easier to do. And I will make it a lot easier than what is in the textbook, okay? So if you read something in the textbook, I will tell you what to ignore, okay, in there, because there's a lot of information there, okay? But before we go into ionic also, there is something else, okay, that we need to talk about, and that is when we talk about all these electrons that are being given, taken, shared in bonding, where are those electrons coming from? Okay, and again, in the previous chapter, we learned about the two kinds of electrons, core and valence, okay, electrons. So the electrons that are responsible here for bonding are going to be the valence electrons, okay, the outermost electrons. The only time the core electrons are involved is in the, fill in the blank. The only time the core electrons are involved are for
groups 1 and 2.
We talked about this when I was showing you how to write the electronic configuration of ions. Right. So the only time the core electrons will be involved in bonding is, what happened? Transition metals. Okay, yeah. Because group 1, 2 through 8, the main group elements are all dealing with their valence electrons, okay? And group number, not group number, the transition metals, okay? The D block are the only ones in which you go into the core, okay, to fill out electrons, all right? So please make those connections, okay, as we go. There are going to be some non-metals also, which we will talk about as far as core is concerned, but maybe not so much, okay? But it really is the transition metals. Okay, how we represent structures when we start doing bonding is by Lewis structures, okay? And G.N. Lewis was the first one who came up with this whole theory of how to show bonding, okay? Otherwise, how do you really show that there are two elements that are bonded, and how do you show that there's an ionic bond versus covalent bond? Okay, so it's really a lot of things that we take for granted really took a long time, okay, to make. So these are called Lewis structures, and Lewis structures are also called the electron dot structures. When you draw Lewis structures, you don't show the core electrons. Okay, you show only the valence electrons in this. They're actually very simple. Okay, I'm just making a big deal out of it because that's what we'll be focusing on. But initially, if you've never seen it, this is kind of what it is. Okay, and so here, for example, if you have sodium, how many valence electrons does it have? Help me out. One. Okay, and so if you have only one electron, then you have to show that as a dot. Okay? So if you remember also from chapter 2, I mentioned to you that if you have any element, there are 4 spots on the corners, okay, of an element. So mass number, atomic number, and then charge, and then the number of atoms involved in bonding. Okay, that's what you write here, the subscripts and the superscripts. Now we are going to focus on these areas, okay, on the top, bottom, and the sides, because this is where you will write these electrons out, okay, so that you are clear in your drawing, okay. So try not to take the corners up, okay, for this. Try to draw them in the left, top, right, okay, something like that. You can draw dot structure if you want, okay. The way I learned it though was like this, at the cross. But the cross has to be a multiplication, not an addition, because if you write addition, that is like a plus, okay? And so plus could be thought of as a cation, all right? So be careful when you draw that. I will draw both, okay? Just so that you are not used to just one kind, you're used to both kinds. Now, how do you draw this dot? Do you draw it over here? Can you draw it over here? Can you draw it here? Can you draw it over here? And yes, you can do it anywhere you want. Okay, no problem. There just to be sure, it has to be some sort of systematic way for yourself to keep a track of things. Okay, so you start from the right, you start from the top, wherever it is that you want to do. But have a system for yourself so you don't confuse yourself, but all of these structures are all fine. Okay, no problem. So this is for sodium, which has only one valence electron. So if you were writing for my favorite for today, magnesium, it would be how many electrons? 2 electrons, and so it would be this. Now if you remember, when we were trying to fill out the electrons, okay, in chapter 8, one of the rules, I think it was Pauli's exclusion principle, that said that you have to fill out singly first, right? Okay, so in those cases, that's how you can do. I particularly don't care which one you do, okay? So long you show me the 2 electrons, that's all that matters to me, all right? But that is also what they were trying to say, okay, is that you fill out singly first and then you can pair up, okay? So if you pair up like this, that's fine. If you want to pair up like this, that's fine. If you want to fill singly like this, it's fine. Or whatever you do, it's fine, okay? If you draw dots, that's fine. Yes?
So it's okay to draw dots, and it's also okay to just put them together.
Perfect. However you want to do it, just make sure that you have them.
Okay.
Okay, yeah. So long you have it. The only problem I have with dots, which is why I don't do dots so much, is because I don't know if it's a speck on your paper or if it's really a dot. So if you're making a dot, make it a dot. Okay? All right. Yeah, make it a nice circle. Okay, so I don't need to do this anymore because it's very straightforward kind of a thing. And that is, group 1 has 1 valence electrons. This is 2, 3, 4, 5, 6. It can't get easier than that. Okay, so group number 7 has 7 valence electrons and so on. Okay, and remember, the maximum valence electrons you can have is, and so we're done. Okay, so 2 top, 2 bottom, 2 on the left and right. Okay, that's about it. Okay. All right, now this is for neutral substances. Okay, what about if you were writing for sodium ion? Okay, what would be the Lewis structure? Well, does sodium ion have any electron? No, so this is it. That's it. Okay, there's nothing else you can do for this. Okay, so you just leave it like that. Chloride ion, how many electrons here? How many electrons? 8, because it's in group number 7, and it took one more electron, so it has 8 electrons. So the way you would write out for chloride is going to be like this, okay? And again, dots or crosses, it doesn't matter to me. Put square brackets around it and one negative outside, okay? The cations, you don't have to put square brackets, okay, anything. You can just leave the charge out there, that's fine. But for the anions, this is what you do, okay? So you write the element, you show the electrons, and remember, for all the anions, you will have a full octet, okay? You will have the 8 electrons there, because that's the whole point, okay, in there, is to get the 8 electrons. So you will have 8 electrons there. So for example, for oxide, it will be the same thing, okay, because oxygen also has 8 electrons. So again, and then 2 minus. Again, there is a very nice worksheet out there for you, okay, to practice on all of this. I don't know if I have it here with me. At least I can show you what it looks like. Because it takes you step by step, okay, into everything. Okay, it's called bonding, and that's what it looks like. Okay, so you might want to print that out and go step by step on writing Lewis structures, and then of course you get into bonding. Okay, with that. So do that for yourself, little practice. Okay. And by the way, if you were writing for aluminum, 3 plus, the Lewis structure for this one is just that. That's it. Okay? Because again, there are no electrons to show. Hopefully, you will not get any Lewis structures to show for the transition metals. Okay? Because when you have transition metals, the electrons are coming out of the core. Okay? So if they're coming out of the core, you may still have valence electrons left. Okay? But traditionally, as we talked about, you're going to remove the valence first. Okay? And then you'll remove the core. So hopefully not. Okay? And so, but usually you will not get, I hope, okay, those structures for transition metals. Okay, are we good with this? Yes. Okay. All right, good then. Let's go on to ionic bonding now. And ionic bonding is very straightforward. The textbook takes you into all sorts of things, okay? If you have your textbook with you, you can open it up and flip the pages with me, okay? But if you don't have it, you can mentally flip the page, okay, if you want. So describing ionic bonds, you can read that up, okay? This is all very good reading, but I don't ask you any of this stuff, okay? The main thing I would like you to know from ionic bond is that it is formed from ions. It is a transfer of electrons. I don't get into the energies involved, okay, in there. The Lewis structures are given here for you, okay, which you can look at that. But otherwise, flip the page. There's really not much, okay. And then it talks about lattice energy, which really you do not need, okay, in there. Section 9.2 is electronic configuration of ions, which I already did for you in chapter 8, okay, because that's when we were doing electronic configurations. So I already did that. So if you want a little review, you can read that in 9.2. And ionic radii also we covered in the previous chapter, not in this one, although I don't know why they would have radii over here, no need for that, okay? So that is, you know, you just need little bits and pieces, okay, from all of this. It doesn't really go into bonding, okay, which is what bothers me a little bit, okay? It goes into all of these energies, but doesn't really talk about what bonding is, okay? And for bonding, as far as ionic is concerned, is a transfer of electrons, okay? So for example, sodium has 1 electron to give, all right? And why does it have that 1 electron to give? We just learned in chapter 8 also that group number 1 is not found in its elemental state, okay? In nature, it's very reactive, okay? So which means it's always reacting. It's always bonded with something. Group 2 can exist by itself, but group 1 cannot exist by itself, okay? So you have to think about why, okay? Why is it that we need to bond, okay? Why is it that, you know, these elements give or take electrons, all right? And that big Y is answered by group number 8. Okay, and group number 8, as we know, is the noble gases, right? We just call them the inert substances also because they don't react with anything. So then you have to think about why they don't react with anything. And they don't because they're
They have an octet.
right. So they have an octet, which is great, but their valence shell is full. Okay, and remember that's the whole reason we talked about valency before. Okay, that the valence electrons are always going to be 8, and if you have 8, then you're pretty happy. Okay, you don't need anything more. So if you have less, you want to take more. If you have very, very less, you want to give that away. So then you don't even have the outer shell anymore. Okay, so the valence shell is gone. So in case of group number 1, if it gives 1 electron away, then it gets to the noble gas configuration. Group 2 can give 2 electrons away and get to the noble gas configuration, and so on. Okay, so the whole goal is to become noble-like. Okay, and this because of stability, and the stability is because of the octet. Okay, you have the 8 electrons in the valence shell, and that's what you need, okay, in order to be stable.
So that's why group 4 is giving plus or minus, because either direction you're going the same.
Because you can give or take, right, depending on what it is being reacted with. Okay, and you will see that the practice problems that I've given you has some both of them, okay, in there. Okay, and so then here, when you get to the non-metals, now at this point, okay, this is where, if you remember also from group number, from chapter 8, which we just finished, is the ionization energy increases, right, as you go towards the right-hand side. So group number 7 can either give 7 of its electrons away, or it can accept 1 electron, which is easier, accepting the 1. Okay, so logically speaking, that's what it does then. Okay, so it will accept 1 electron, here it will accept 2, accept 3. Okay, rather than give the 5 away in order to become stable. Okay, because ionization energy is too high. So keeping those logical things in mind, then we can understand this a little bit better. Okay, as to why bonding occurs. So here when we talk about ionic bonding, and we have sodium, which is ready to give 1 electron, and then we have something like fluorine, which has 7 electrons, 3, 4, 5, 6, 7. And if you have different colors, it's always nice to have one element in one color and the other one in different color. If you don't, that's okay too. Sometimes what I do for myself is you can draw it like this. So that way you know that 1 electron is coming from the other element. Okay, just so that you can keep a track of your electrons. But essentially what's going to happen in an ionic bonding is the sodium is going to lose the electron and fluorine is going to gain the electron. Okay, so essentially this is how I show it. This is how it goes. So sodium now is plus and fluorine has gained that electron. So fluorine is 7 and then plus 1 and that. There are 2 most important things in bonding. Okay, one is that you should know how many atoms are going to bond, okay, with each other. Here, sodium had 1 electron to give, and fluorine needed 1 electron. So which means you need only 1 and 1, okay, of both. Now, previously, how you have done this was like this, if you remember. Right? That's how you did this. You can still use that method. That is still fine, okay? So that is the one thing that is important is what is the ratio of the atoms, okay, in there. So this is very easy in ionic bonding because you have ions, you have the charges, and you can just do the crisscross, okay? It gets a little bit harder in the covalent, and I mentioned that to you before also in chapter 2, okay, that I will have to give you the structure of the covalent compound, okay? You cannot figure it out because you can have carbon monoxide or you can have carbon dioxide. Okay, so you don't know which one I'm talking about. So I will have to give you that. Okay, so that's the one thing that you have to do is figure out the ratio of the elements. The second thing that you have to do is show the Lewis structure. Okay, once the bonding is done, then you write the Lewis structure. And what's the Lewis structure here? It's going to be this one right here, the one that I've shown. Now, if this is bothering you, okay, that how could they be bonded, you can draw them a little closer. If you feel like that makes a difference. but that's really what it is, okay? Because one element has given the electrons, the other one has accepted, transaction over. That's it, okay? So there is nothing that is actually holding them together except for what is called the, anyone remember? This is something we talked about in chapter 4 when we were doing electrolytes. I know. It's one of those words, you know, it's like, what? Really? We talked about this? The electrostatic force. Yeah, we never talked about it again, you know. But electrostatic force is the force between positive and negative, and it's a very, very strong force, okay, because it's a attraction between the opposites, okay. So electrostatic force is what holds all of these together, okay. So let me just show you one thing here real quick. Since we do have all of these crystal structures here, and the reason that we have all of these bonds here is just so that it can hold it together, okay? But essentially, if you pick up a crystal of sodium chloride, like the one in your homes, okay, for salt, if you pick that up, there are no lines there, okay? They're going to be all compact, everything is next to each other, and then there will be a sodium, there will be a chlorine, okay, all associated together. How they're boxed together, that's something that you learn in GenChem 2, okay? Are they going to be this way, or are they going to be this way? Okay, because these two structures are different, right? You can see that. So in the crystalline structure, and that's what the lattice energy is all that, okay, what they're talking about. And this depends on the size of the anion or the cation, which is why we study the sizes, okay, of cations and anions. Will you get this kind of a crystal structure, or will you get this kind? Okay, so this comes from the size of each of the ions that's forming the structure. So you can have something like this, which is, you know, this is a cube, and this is called a face-centered cube, okay, because there is an atom in the face, okay, of each of these. But in this case, the face is empty. You don't have anything here. So it depends, okay, what kind of a combination you have. And again, then don't forget, because you can also have things like calcium chloride, right, where you have two chlorines with one calcium. So here you have two anions and one cation, or you could have something like aluminum oxide, where the ratio is 2:3. Okay, and so all of these will form crystalline structures, and they are held together by the electrostatic force. Okay, and that force is very, very strong. Okay, extremely strong, and that's the energy that they talk about in here. Okay, but I will not go into it, but that's what it is. Are we good? Okay. So when you're supposed to write me any structure, okay, any Lewis structure for ionic compounds, so if I say, give me the structure between magnesium and oxygen, okay, so if I say something like that to you, show me the Lewis structure for this, all you know that magnesium is 2+, you know oxygen is 2-, okay, and so then you can do the crisscross if you want, and then you know that the ratio is 1:1. Okay, that's how you know the ratio of the elements. And once you know the ratio of the elements, then you can go ahead and write the Lewis structure. If the ratio is not 1:1, then of course you have to indicate somewhere as to what that would be. So let's go ahead and take aluminum oxide. So between aluminum and oxygen. Okay, how you would do this? So aluminum is 3+, oxygen is 2-, so you do your crisscross and you get your ratio. Really, this is the best way, okay, to do the Lewis structure for ionic compounds. If there's a better way, you come and tell me, okay? But this is the best way otherwise to do Lewis structures. So now you know that you have 2 aluminum, okay, in there. So if you want, you can write the individual ions first. So you have the aluminum, which is 3+, you have the oxygen, which is 2-, and remember all the anions, okay, 90% of the time, they're going to have 8 electrons, okay, 90% of the time. There are still some exceptions, but otherwise they will have full octet. here. But now we have to write the ratio also, okay, because aluminum is 2 and oxygen is 3. Okay, so all you have to do now is this. So you take the subscripts and you put them out here, okay, in front. That shows you that you have 2 aluminum ions and 3 oxygen ions. Good? And that essentially is ionic bonding. It's very simple, it's very straightforward, okay, there is not much to it. Good? One of your tasks, believe it or not, okay, for me, when we get into bonding, is for you to identify whether you have covalent bonding or ionic bonding, which is something that we've done in chapter 2, okay? But we somehow seem to forget that, okay? When we get to chapter 9, suddenly we've forgotten everything, okay? So one of the things that you should always do for yourself, when I ask you to write me a Lewis structure, okay, so if I say write me a structure for NO, your first thing, okay, just like you did with the nomenclature, is to figure out what elements do I have. Do I have metals, non-metals, okay, what do I have? And that should be your approach still, okay, and that would be the best approach, very logical approach. You can't go wrong with that, okay? So that's when you will know how to draw the Lewis structure, because the Lewis structure for covalent compounds is very different than for ionic compounds, okay? All right, good. Any questions for ionic? Keep it simple, okay? All right. Good. I have one shortcut. Of course, you know, we always have shortcuts, okay, for everything. And this is a very useful one, okay? And that is with these electrons, okay, over here. So if you ever get tired of drawing all these crosses out, which we always do, okay, is that you can actually write lines, okay, for this. And the way we do this is like this. So each line represents 2 electrons then, okay? So then you're out of the dots and crosses. If you were writing the Lewis structure for chlorine, let me come back. I didn't do that, did I? No. Okay. So if you were writing the Lewis structure for just chlorine, not the chloride ion, just the chlorine, then you would have the 7 electrons there, okay, because it has 7 electrons in the valence shell. So you can draw them like this. So you can pair up all of them and leave one of them unpaired, okay? So these ones over here, these all represent 2 electrons, and this poor thing is by itself then, okay? Again, cross or dot. Myself, as an organic chemist, I don't like the dots, because when we get to organic, there's a whole other part of chemistry that you'll be introduced to, okay? And so I don't like dots that much for that reason. But if you give me dots, I won't hold it against you, okay? Only when you get to organic, then we'll handle it. Okay. Move on to covalent. Yes? Okay, let's move on to covalent. If you're at the bottom of your page, I want to get on a new page. Because when we write all these structures, although I have only 5 minutes, I will only be able to do a few, but for continuity's sake, okay? Because we'll start today, we'll go on. So if you're at the bottom, try to start at a new page so you can see all the structures right in the first one. So covalent compounds are different. Covalent compounds are made up of non-metals, okay, and then there is sharing of electrons. So which means we don't have to write cations or anions, okay, in there. There is no give and take, okay, of electrons going on, which means you have to figure out the sharing aspect. The principle is still the same. Principle meaning octet, okay? You still have to get to the stable octet. You still have to make sure that each atom has 8 electrons, okay? Eventually we're going to learn some exceptions, but the goal is still to be 8, okay, in there. Except, here is the first exception. For hydrogen. Can hydrogen have 8 electrons? It has only 1 shell, right? So it can have only 1 electron in that, well, 2 maximum, okay, in that shell. So hydrogen is what we call, it has a duet rule, okay, not an octet rule, it has a duet rule. So which, again, if you want to forget that word, that's fine. All right, so here is a hydrogen with 1 electron. It needs 1 more electron, okay, in it. So it will find another hydrogen atom which also has 1 more electron, one electron. And then both of these can be shared. When I teach, I do all these drawings for you, but this is not the Lewis structure. Okay, this is just explaining to you what the process is going on there. So when you need to show what the sharing looks like, here is what you can do. You can circle it if it makes you feel better. Okay, you don't have to. You can also draw it like this, and the ultimate. There. Okay, so we want to make sure that both of the atoms, they have the requisite number of electrons, okay, in them. So in case of hydrogen, you can only have a maximum of 2 electrons, okay, in there. So if we were counting 8, that'd be different, but we're counting 2 electrons. So the best way to look at for sharing electrons is look at one atom at a time. So when you look at this hydrogen, it has 2 electrons. And if you prefer this one, you can look at this one, okay? So you have one hydrogen here with the 2 electrons, so it's good to go. And then you look at the other hydrogen, and then this hydrogen has the 2 electrons, so it's also good to go, okay? So that's how we approach covalent bonding and the sharing of electrons, okay? Now, there is something about sharing, okay, and that is goes sharing in your home also, is sharing is sometimes not fair, okay? And in some cases it's fair, in some cases it's not fair. When you have similar atoms like this, hydrogen and hydrogen, then this is called equal sharing okay, of electrons. So when we get later on, when we have different atoms in there, then we'll have a different kind of sharing going on, okay? But right now, this is what we call equal sharing of electrons, so we can write like this. Even the other ones we can write like this, but we know, okay? We know what's going on. So here, this is equal sharing, and this is hydrogen, okay? As we know, this is the Lewis structure. You can write any of these structures. These are all fine, okay? I would prefer if you don't circle, okay, to draw the Lewis structure. That is a good way to have your process so you can see how you are sharing the electrons, but that's not your final structure, okay? All right.
Would you prefer, when we're doing the Lewis structure, if we did the line, would you just do it horizontally or can we do it vertically?
No vertical, okay? Not in these cases, okay? Yeah. Try to do horizontal. Vertical is not very good, okay? We leave the verticals primarily for the lone pair of electrons, okay? The lone pairing meaning like this, okay? Where you have the pair like this. That's what we leave it for, yeah. Between the sharing, it's nice to see it like this, okay? Nice and clear, okay? And I think it's more of a drawing thing than anything else. I mean, it's not wrong, okay? But it just looks much nicer this way. Okay, so another one, let's take chlorine. Chlorine also, as we know, is Cl2. Okay, we'll do this quickly. We'll do this with the last one. So chlorine has 1, 2, 3, 4, 5, 6, 7 electrons. And so does the other chlorine. That doesn't change either. Each of them is short 1 electron, okay, in their valence shell. So each of them then decide, okay, let's share 1 electron each. And so then you have this, and if you're already tired of drawing the crosses, as I am, this is how we do it. Both of these structures are fine. You can draw either of the Lewis structure. And then at any given time, okay, as you can tell, that this chlorine right here is going to have 1, 2, 3, 4 pairs of electrons, 8. And then you can cover the other one up and say this is also 8 electrons. Okay, so again, there is equal sharing going on. So these are simple molecules, just the diatomics. Okay, so you can do the same thing for fluorine and oxygen is a little different. They're only sharing 1 electron here. But and then so hydrogen likes to share that 1 electron, and so you can write your Lewis structure like this. You can write it like this, or the best way is to write it like this. Okay? And of course, you know my philosophy as we are going through all of the structures that I will draw for you today. leave a little space, okay, in the middle somewhere so that we can come back and write more stuff, because we will write more stuff. The other one I did for you was chlorine, correct? Cl2? Okay. So Cl2, which means chlorine, 7 electrons. And then share 1 electron. There, that's that. Cl, Cl, and then you can have all of these electrons as lines. We talked about the lines, correct? Okay, so one pair of electrons is represented by that one line. Okay, so here is hydrogen, here is chlorine. You can also have a bond between hydrogen and chlorine, because that would be hydrogen chloride. Okay, and so if you were to write the Lewis structure for HCl, okay, then you would see how many electrons each of them has. Hydrogen has 1, okay, and then if you want to have a different color, go for it. Okay, chlorine has 7 electrons. Share the 1 electron. And here we are with hydrogen, chlorine, Cl, 1, 1, 2. There. And by the time the bonding is done, you really can't differentiate, okay, between one electron and the other. So then, here is what we have. Okay, Cl, that's the Lewis structure. Again, let me remind you, for Lewis structure, it is really imperative you show all of the electrons, okay, in there. So whether something is bonding, not bonding, whatever it is, all the valence electrons have been shown. So here, hydrogen has no more electrons because it is being shared, okay, and for chlorine, 1 is shared and the other ones are not shared. So you got to show all the electrons. Good so far? Then let's go on to oxygen. Oxygen is O2. Oxygen can also be O3, as we talked about before, okay, with ozone. So, but we're going to go for O2 first, and oxygen has 6 electrons, okay, and again, just look at the group number. It's in group number 6, so it has 6 valence electrons, 1, 2, 3, and if you want to write it like this, you're most welcome to. If you want to pair up all the electrons, that's okay. Both are fine with me now, although you know that they are filled singly first. Oxygen has 6 electrons, it needs 2 more, okay, in order to be stable. Remember, it's all about forming the octet, okay, 8 electrons, because 8 electrons are the most stable ones. And so you share 2 electrons over here. So oxygen, 1, 2, 2 electrons from each of the oxygen that is being shared, and then the 4 electrons are left behind. There. And if you want to get rid of all of the crosses, then of course, this is what you do. Can you do this? Sure you can. If you want to draw smiley faces, just kidding. All right. Okay. All right. Good?
What do you do to write one dot on the bottom and one on the right?
It doesn't matter where you write them. It doesn't. Not at all. So long you're sharing the right number of electrons. Yeah. You can write them wherever you want. Nitrogen, which is N2. And again, remember, for all of the covalent compounds that we're writing the structures of, I will have to give you the formula, okay, for covalent compounds. Ionic compounds, I can ask you to write the formula for me because it's a lot simpler. You do the crisscross and you write it. But for covalent, I have to give you the formula. Otherwise, it'll be hard for you. Okay, so nitrogen, N, and that is 5 electrons. The next nitrogen also has 5 electrons. And this is really weird to show how it's being shared. And actually, Jeffrey, that's what I was doing before. I was trying to write them in such a way that I can show the sharing properly. Okay, there was no other method there. So here it will be hard for me to show this electron being shared, right? Yeah, it's going to be tough. But anyhow, it doesn't matter. You understand the concept. So when we have 5 electrons, we need 3 more, okay, in there to be shared. So 3 more for both of them. So therefore, 1 electron here, 1 electron here, 1 electron here. It doesn't matter which one is which. 3 electrons are being shared. And so therefore, 1, 2, 3, 1, 2, 3. Write it like this. Initially, as you're learning, it's always a good idea to write like this. Once you get good at this, then you don't have to anymore, okay? Because this one shows you clearly how many electrons are involved, okay, and how to write things out clearly. After a while, you'll get used to it and you won't have to do it again. So then we have 3 electrons being shared, 3 pairs being shared. So here are the 3 pairs, here is the other nitrogen, and then you have the pair on the top. Okay. What I'm trying to do here is I'm trying to give you several examples of small molecules, okay, that you can write out. So these are the diatomic molecules that we've talked about so far. And now I'll go into a little bit more, not complicated, but more than diatomic, okay? So for example, let's go ahead and write for CH4, which is methane, okay? And so for methane, now you have 5 atoms. You don't have just 2 atoms anymore. When you have 2 atoms, you really don't have much to think about because you just need to join them together, right? And make sure that when they share the electrons, both of them have 8 electrons, okay? Or 2 electrons in case of hydrogen. But when you have something like CH4, then you have to start thinking, how do I do this, okay? The first instinct generally, okay, is when you start seeing something so large or with so many atoms is to do this. Okay, just write everything out in a line, okay? And that's not the way to approach all the Lewis structures, okay? So the rules of the Lewis structures are very straightforward, and one of them is you have to have a very compact structure, okay? And a compact structure is, of course, very small, okay? So it can't be in a line like this. And especially at this level for you, it's not going to be this kind of a line thing, okay? Eventually it gets there, but not right now. So it has to be compact. So if it has to be compact, then you have to figure out, okay, how do I make this small? The second rule is try symmetry as much as possible, okay? So your final structure should come out to be very symmetrical, okay? One of the reasons I write all of this out in such a way is just to show you a little bit about symmetry. And so diatomics, you don't see much symmetry, but once we get into a little bit more of the larger molecules, you really have to watch out for symmetry, okay? And try to follow that because it will make your life a lot better. So between carbon and hydrogen, you have 5 atoms then. So the first thing you have to decide is what has to be my central atom, okay? So you want to say?
Carbon?
Because?
Because it has 4 or valence electrons.
It's very good. Because it has 4 valence electrons, and that has something to do with it, which means it can?
It can accept more. Or
It can accept more. Okay, so that's the thing, all right? It can accept more. Generally, for me, my rule is the more it is on the left-hand side, the more chances it's going to be in the center. Okay, so the more it is on the right-hand side, then the more it is going to be terminal or outside. Okay, and as we go on and as you get more practice, I will tell you more rules and more shortcuts. In the end, I'll give you a lot more shortcuts. Okay, so let's say that we have carbon in the middle. And we have 4 hydrogens, so write out the 4 hydrogens all around it. And then go ahead and fill in all the electrons. Okay, so carbon has 4 electrons, so go ahead and write those out. And then hydrogen has also 4 electrons, 1 each. So here you can write that. And then now it becomes very clear how you're going to share the electrons. Okay, so they're not that complicated.
are you supposed to write them like on top of each other, or can you write them next to each other?
Right, so next to each other, are you saying something like this?
No, I mean the electrons themselves, like the X's.
It doesn't matter how you write it. Yeah, it honestly doesn't matter so long you show that they are being shared. Okay, so now in this case, I was trying to show you how it's happening or what the electrons are. So in the next one then, if you do this, that's what you're wondering, right? Like this,
Yeah.
like this, like this. Sure, you can write like this if you want. Okay, and that's fine too. Both of them are correct Lewis structures because it shows you the total number of electrons and how they're being shared. Okay, so you can write it whichever way, and then of course the best way is yes, the line structures. When you write these structures out, please do me a favor and write them as symmetrically as possible. It will really help you in the next chapter, okay, a lot. So write them as symmetric as possible. When you asked me the question before, Samara, I thought you were asking me something like this, and I was gonna say don't do like this because this looks like chicken feet then. Okay, so that's not a good way, okay, to draw a structure, yes.
And also, if you do it like that, doesn't that affect, like, if you do it that way, there's a certain way you do it for its shape of the...
That's what I was saying. So in the next chapter, it becomes a lot easier.
Yeah.
Okay? So this is not a wrong Lewis structure because technically you're showing all the electrons. Okay? This Lewis structure is right, but first of all, it looks so weird. And then second thing, it doesn't really help you in your learning in the future. Okay? And so it's much better to learn something correctly and something that, you know, will help you later on. So that's not a right structure. Okay? Right there. Good. Moving on. Next molecule. Okay. So let's take ammonia. And again, I hope you're leaving some room in the middle because we'll need to come back. Okay, and I'll have to write some more stuff in there. Okay, ammonia. So between nitrogen and hydrogen, which atom is my central atom? Everybody? Nitrogen. Okay, because it's in the left. It also has a higher valency. Okay, that's how I look at it. It's capable of sharing more electrons. So nitrogen and then 3 hydrogens. How you draw that hydrogens is up to you. You can draw them top, bottom, whatever. Just don't draw them like the chicken feet like we did before. So then nitrogen has 5 electrons. 1, 2, 3, 4, 5. And then hydrogen with 1 electron each. There. And again, whatever is suitable to you. Okay, if you feel like circling these two to show that these are being shared, it's up to you. I'm not doing it anymore because I think you all get it. Okay, and so, but if you feel like it, you're most welcome to circle that. And here is our structure then. And if you want, you can also turn it upside down, which means draw it something like this, which really is how I draw it usually. Okay, with the extra electrons on the top, not at the bottom. Okay, so that's for ammonia. That's the Lewis structure.
Would it be incorrect to draw a horizontal line between the bottom hydrogen and the nitrogen? Or like should you always draw it vertical if it's on the bottom and the top?
That's what we were talking about last time, yeah. Try to do verticals, okay? Yeah, it's a lot clearer that way, yeah. So it's much more visible. Okay, so then let's go on to water. Another lovely molecule. Why don't I give you 30 seconds to draw that one out? Put whatever you want to in the center. And once you're done with water, try out carbon dioxide as well. So water was not an issue. You all drew the 6 electrons and then with
just carbon.
hydrogen, so that's great. Okay, everybody has that, no problems. Here we are. Some of you drew your structure like this, and that's okay as well. Okay, it's not a big deal. It's still quite symmetrical, all right? The way I look at my structures, when I especially have so many electrons, and usually you will have 8 electrons, is to draw all of 8 of them symmetrically. Okay, so whether they are across from each other or like this, that's fine. Okay, for carbon dioxide, what's in the center, carbon or oxygen?
Carbon.
Very good. So carbon, 4 electrons, and then oxygen has 6 electrons. How many does oxygen need? 2. And carbon needs? 4. So you answered your questions yourself. Okay, so all of you are almost showing, I think, a single bond in there. All right, what you need to do is share 2 pairs of electrons, okay, because oxygen needs 2 electrons. All right, so then you will share the 2 electrons from oxygen and then 2 electrons from oxygen on the other side. So all the 4 electrons of carbon then are shared, okay, over here. And so you have carbon, 2 electrons. Let me write the electrons first, then we'll write the lines. So 1, 2, and then oxygen with 1, 2, 2. And then much clearly, this is what you have. So you have nothing that is left on carbon that is not shared. Okay, all the electrons are being shared on carbon. Good? Okay, learn to share as much as possible and try to get the octet. That's the goal. Okay, so that's what you were missing, is the octet. Okay, let's go ahead and write some more words, okay, so that we are clear in what we're talking. Even when as I'm talking right now, I feel like I can't say some words because I haven't really talked about it, okay? So let's go ahead and fill those in. So I can start with here if we want, or let's start here with HCl. Okay, let's go back to hydrogen chloride. In hydrogen chloride, there are a few things that I want to mention. One thing is there are two kinds of electrons here. Okay, one, these are what we call the shared electrons, and these are the not shared electrons, which means they're also the non-bonding electrons. Okay, so two kinds of electrons. You can call them whatever, but you have to be able to distinguish them. Okay, so these are over here bonding electrons, and then these ones are the non-bonding electrons. So there are two kinds of electrons, first of all, in a lot of compounds. Okay, and now when you look at all your structures, you can probably see that. Okay, here also in oxygen, these are the bonding electrons, and then these are the non-bonding electrons, nitrogen, bonding electrons, non-bonding, and so on. Okay, and then sometimes these electrons, the non-bonding electrons, you will see that a lot of them actually occur in pairs. All right, because they're just drawing a line. There's hardly any single electron that is left behind, so everything is almost paired up. So we actually sometimes end up calling it the lone pair of electron. It's not that lonely, don't worry. It's got, it's a pair. So lone pair of electron. So how many lone pairs do we have here in oxygen?
4.
4 lone pairs, okay? 1, 2, 3, 4. 4 lone pair means that you have a total of 8 electrons that are non-bonding, okay? How many electrons in the bonding here?
4.
2 times 2, right, 4, okay, over here. So this is something that you will have to do, okay, by the way, is to figure out how many bonding electrons, how many non-bonding electrons you have, okay? So this is a good practice to do. So lone pair of electrons, so anything you can call lone pair of electrons that is not bonding. Here for nitrogen, you also have 1 lone pair of electron on each of the nitrogen. Okay, and then you have the 3 pairs that are being shared. Good so far? So that's one classification that we do. The other classification that I want to talk about is the bond here itself. Okay, so the bond here is called a single bond. And a single bond is 2 electrons that are being shared. In oxygen, this is called a double bond then. And here we have 2 pairs of electrons that are being shared. And if you want, you can write here 1 pair, if that makes you feel better. 1 pair of electrons or 2 electrons. So in a double bond, you have 2 pairs. And then we have nitrogen, which is, yep, triple bond. And that's 3 pairs of electrons. So 2 things, okay? The bonding electrons, non-bonding electrons, and then the type of bond you have, single, double, and triple bond. There is nothing like a quadruple bond, okay? Nothing like that. So the maximum we can share is 3, okay? Pairs of electrons, that's it. So once you get to something like this, okay, where you have carbon with 4 bonds, it's really just carbon with 4 single bonds. Okay, that's all it is. It's nothing really different. Are we good so far? Yes.
So for oxygen, you have 2 pairs of lone electrons?
2 pairs.
2 pairs?
2 pairs on each of the oxygen. Yeah, so total of 4. And usually that's what the question will ask you. Okay, is draw the Lewis structure of this compound. How many lone pairs do you have? Okay, so that's the total of lone pair of electrons. Or I will ask you how many do you have as bonding electrons. So then you look at you have to be very careful. Is it asking you for pair of electrons or total number of electrons? Okay, yeah, that's something you have to watch out for. Other than that, it should be pretty straightforward. Usually they ask for how many lone pairs, but anyhow, so that's what this is. So depending on what kind of a structure you have, you can have single bonds, double bonds, triple bonds, okay, and then here, so you have 2 double bonds, okay, between carbon and oxygen. So let me give you one more structure, okay, that you can write the Lewis structure of. Try this one, HCl. Between carbon and nitrogen, what are you going to put in the center? Carbon. Okay, again, because carbon has higher valency, or you can say carbon is more on the left-hand side in the periodic table. Are you ready for the answer? Okay. So carbon in the middle, nitrogen on one side, hydrogen on one side. And here's another clue, okay, for you guys for covalent compounds, is that because I understand how complicated it can get sometimes, okay, is I will try to give you, if I have many atoms in there, I will try to give you in such a way that you will have to draw it also in that way, okay? So don't try to move the hydrogen around, that's what I'm trying to say. Just leave it as it is, write it out, draw all the electrons, and then see how many to share, okay? So don't try to move any atoms around, just write them like that, and then fill in all the electrons. So carbon has 4, nitrogen has 5 electrons, carbon needs 4 electrons, so it will get 1 from here, and then it still needs 3 more, so then it can share 3 from here. How beautiful is that? Okay, and then 1, 2, 3 there, and then the lone pair that is left on nitrogen. Okay, that's the structure. So here carbon is 1 bond here and 3 bonds on this side, exactly, triple bond on that side. And the reason I show you this is just to give you an idea of how many multiple bonds carbon can have. Okay, so you see carbon there in methane with all single bonds, you see carbon here with double bonds, and you see carbon here with triple bonds. Okay, so you can have carbon multiple ways because carbon is capable of having up to 4 bonds. Okay, in what combination it's going to have, you can decide that. Okay, depending on what atoms are given there.
So because carbon's in group 4, it can have 4 bonds, and nitrogen's in group 3, it can have 3 bonds.
Very good, you're getting the gist now. Yes.
Or in group 5.
Well, group 5, yeah. And 3 you're saying because you're thinking about -3.
Yeah.
I know, and that's fine too, okay? And so the way the book is going to tell you how to write Lewis structures is a little bit more complicated, and I do that when we get into a little bit more complicated molecules, but I like to keep things simple, okay? And the best way to do is kind of how I've been going over this, which means that if you have a larger molecule with more atoms in there, you figure out first what's your central atom, okay? Which whatever is on the left-hand side is in the center, okay? Group number 7 and hydrogen. Halogens and hydrogens, they will always be terminal atoms, okay? And I think this is given to you in the PowerPoint also. I've given all these clues for you. So when you're drawing this out, okay, you will never, ever have anything like this. It's not possible, okay? How many electrons does hydrogen have here? Technically 4, right? Because it's sharing 2 from here and 2 from here, and that's not possible, okay? Because hydrogen is capable only of having 2 electrons, all right? So that's not possible. The same thing happens with chlorine then. So chlorine, fluorine, all of these, okay, they can have only 1 bond, okay, so far. Okay, we're going to change the rules later on. But right now they can have only 1 bond, which means hydrogen and halogen, always terminal atoms, okay? Okay, one more thing I want to show you is for oxygen. Look at oxygen here, you have 2 single bonds on oxygen, and here you have a double bond on oxygen. Okay, so again, because oxygen is capable of having 2 bonds, it can have those in 2 single bonds, and it can have that in a double bond, okay? Similarly, nitrogen, okay? You can see nitrogen in single bonds, and you can see nitrogen in triple bond. Nitrogen can also be a double bond. I just don't have an example for you here, okay? But it can have double bond as well. So you can have variety of all of these bonds, okay? So when you look at a structure, you approach it very systematically, okay? And then remember your rules. Carbon has to have 4 bonds to be happy, nitrogen has to have 3 bonds, the way I think of it is I just look at the periodic table and I see carbon is here. I need 1, 2, 3, 4, okay, for it to be happy. Nitrogen needs 1, 2, 3. Oxygen needs 1, 2, that kind of a thing, okay, to that many bonds. That's all it needs. Okay, so that is for small molecules, normal molecules, nothing very different there. However, there are some exceptions, okay, in here. So let me go ahead and mention the exceptions to you, because the worksheet I have for you does have some in there. Okay, so we need to write those out. I'll leave this on here. Maybe I may have to erase it. Here. There are 3 exceptions to octet rule. And exceptions to the octet rule means that you don't have 8 electrons. Okay, and so when you don't have 8 electrons, you can have less or more electrons. So that's the first 2 we will tackle. The first one is incomplete valence shell. So which means that these are compounds that actually have less than 8 electrons, but they're still happy, they're still okay, right? It's still, life is still good. And the most common example that you will find here is for boron. Boron is in group number 3, and remember it is a metalloid. Okay, so it is a non-metal. And there is a common example for boron, BH3. BH3 does exist, just like NH3. Okay, so BH3 is kind of similar to NH3, but once you start writing the Lewis structure for it, which go ahead and don't wait for me, go ahead and write the Lewis structure. And if you're writing dots also, that's fine with me. Okay, it's not an issue. So then you have boron with 3 bonds with hydrogen. And so how many electrons does boron have right now? 6 electrons, because it is sharing only 3 pairs of electrons. So that's an incomplete shell, right? Because technically it can take 2 more electrons, all right? And because of these exceptions, some of these molecules have different kinds of reactivities. You're going to learn that later on. Okay, some you're going to learn in GenChem2, some you will learn in organic, that some of these molecules end up having reactivities because of this exception, okay, in there. So boron is one of those. So what I'm trying to say to you is when you find these structures, okay, and you're writing these structures out, don't be shocked, okay, that, oh my God, what am I supposed to do? It doesn't have 8 electrons. That's fine. It may be one of those that has an exception to it, okay? All right, then the second one is where you have an expanded valence shell. An expanded meaning more than 8 electrons. Now this is a little bit weird one because we don't think about expanded shells. For us, valence shell has always been 8 electrons. That's it. The maximum you can have is 8, all right? So we don't think about having an expanded valence shell. So I'm going to go ahead and take phosphorus, okay, in there. And phosphorus, this is a normal compound you would write for phosphorus, okay? For example, phosphorus trichloride, okay, which is pretty normal. And if you write the Lewis structure for this, it will be P, and then you have the 3 chlorines. And if you're fast now, how do you feel? Comfortable now? Writing these structures a little bit, getting there? Okay, all right. So phosphorus with the 3 electrons being shared and 1 lone pair left behind because it has the 5 electrons. And then the chlorine, of course, has the 6 electrons left over. So that is PCl3. But there is also a compound which is PCl5. Phosphorus pentachloride. Again, phosphorus pentachloride means you have 5 chlorines attached. So here phosphorus, which has 5 electrons, all of them are going to be shared with chlorine then. Okay, because now you have 5 chlorines in there. So Cl, 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 and then Cl. And if you don't mind, I'm going to go ahead and write lines here. and just show the one electron that is being shared for for chlorine. So 1, 2, 3, 4, 5. And this is a young man doing exercise. Aerobics today, that's what it is. So here is phosphorus in the middle, and then we have chlorine, chlorine, chlorine all around. Okay, and again, lone pair of electrons on chlorine. Okay, so the Lewis structure is not a problem. Okay, because sure we can share all the electrons. What is the problem with this is the 10 electrons, okay? So how can phosphorus have 10 electrons? Okay, that's a big issue because technically we can have only 8. So phosphorus can have PCl5, but here also let me tell you, nitrogen cannot have NCl5. Okay, nitrogen, NCl3, which is nitrogen trichloride, possible. We just drew out a structure for ammonia, NH3. Okay, so if NH3 is possible, NCl3 is also possible, but NCl5 is not possible. Okay, so nitrogen pentachloride does not exist, but phosphorus pentachloride exists. So then you have to think, why? Okay, why is this happening? So then you come back here to the periodic table, all the answers are here. When you are in the nitrogen group, okay, over here, not in the group, in the row over here, what shell number are you filling? Shell number 2. Okay, so this is shell number 2. What orbitals do you have in shell number 2? S and? That's it. When you get to shell number 3, what orbitals do you have? S, P, and D. You're not filling D until you get here, but it's there, right? Technically it's there, you just didn't start filling it. So when phosphorus combines with 5 chlorines, then the extra electrons actually go into the D orbital. Okay, in there.
So wouldn't that technically wouldn't the D orbital be the valence shell? So wouldn't that technically make it incomplete?
No, well, it's not incomplete, it's an expanded shell, because technically when you do bonding, you're supposed to have an octet. And so you're keeping your octet in the middle, anything less than that and more than that.
Oh.
Okay? Yeah, it's not about the D being incomplete. Got it? Okay, yeah.
So is it because you have that 8, so you have the octet, and then there's 2 more, so that makes the next shell a duet?
Not the next shell.
Or the
next orbital.
The orbital
D
a duet.
available. Yeah.
Does that work with more?
It works with more. Okay, good thing you asked. Because here it is. You can have that with sulfur also. Okay, because all of these now, they all have D available to them. Correct? None of these ones in the second group. If you have a second shell, you don't have D orbitals. So these ones cannot have expanded shell. However, once you start getting into the third shell, then you can have expanded shells. So phosphorus has it, sulfur has it, chlorine has it, and anything down here, they're all capable. Whether they have it or not, that's a different thing, but they're capable, okay, of having expanded shell. So sulfur, for example, because it has 6 electrons in the valence shell, you can have up to 6 sharing going on. So 6 sharing meaning 6 pairs, which means you have 12 electrons, okay? And chlorine, which is 7 electrons, and if you share all 7 electrons, that means a total of 14 electrons, right? Okay, so that's a lot of electrons, all right? But there is a place for it. Okay? There is a place for it. So that's the expanded shell, okay, in there. The last exception is when you start having an unpaired electron. In all of these structures that we've written out so far, everything has been shared, shared, shared. Okay, whether you have a lone pair of electron, it is still a pair. Whether you have electrons that are being shared, in which case they are shared, so that's a pair. So everything we've been drawing out line, line, line. We haven't left anything that is not shared. So when you do have the unpaired electron, that actually becomes an exception. Okay, and that happens a lot when you're dealing with nitrogen group, because nitrogen has 5 electrons, and sometimes also in group number 7, because those are odd number of electrons. So not everything is shared in those cases. So for example, if you were to write the Lewis structure for NO, nitrogen monoxide, Nitrogen again, 5 electrons. Oxygen has 6 electrons. Oxygen needs 2 more. So you at least make oxygen happy. So nitrogen with 3 electrons left over, 2 bonded, and oxygen then has these lone pairs. So let me go ahead and write that all in lines except for this little poor thing which is hanging out by itself now. So that's an unpaired electron, and that is an exception. When you have exceptions, these compounds behave a little differently, and nitrogen oxides, they do behave differently. So if you have any electron left behind which is not paired, check your structure, okay? Make sure everything is paired. If it is not paired, then see maybe it is one of those exceptions, okay? And then usually, as I said, nitrogen, group number 5 and 7, they're going to have those exceptions. Excellent. Are we good? Getting comfortable? Yes? Nodding heads, that's good enough. Okay. Excellent. Then let's go on to the reason I'm telling you all of this, okay, now instead of giving you the worksheet, because I do have a wonderful worksheet for you today, which we'll work on in 2 minutes, okay, as soon as I get with the other part, is some of the things are in there. Okay, so I need to give you at least one example of it, okay, before we go on. So we have the normal Lewis structures, which are like this, follow the octet rule. Then we have this, okay, which is the exceptions to the octet rule. And then the third, okay, which is also an important part, is polyatomic ions. Okay, you remember those? Chapter 2. Okay, so many of them that we had back then. So when you have polyatomic ions, you also have Lewis structures of those, obviously. Okay, so let's go ahead and take a simple one. So for polyatomics, let's take carbonate ion. CO3, 2 minus. There are a couple of ways to approach this. One is the scenic route, one is the short way, of course. Okay, there are always 2 ways to do things. And as you get comfortable, then you use the short one. Okay, the scenic route is when you count all your electrons, okay, which is what's given in your textbook also. And I really like it when you're doing polyatomic ions, okay, because polyatomic ions can get a little complicated. On page 354, write down the page number in case you do have a textbook. These are the rules. And I think I've given those in the PowerPoint as well, okay? So these are your rules, so I'm gonna go over them, but I'm not writing them, okay, out for you. So in this one, what you do, especially, it's really good when you start having polyatomic ions and you're just learning this, it's good to follow those. So the first thing those rules state is you count all your valence electrons, okay, that are available to you, okay? So we're going to do this mathematically, okay, with the number of electrons. So we have carbon here and we have 3 oxygens, good? Okay, so we're going to count all the valence electrons. Carbon has 4. Let me write it like this. So 4 electrons, and then we have 3 oxygens, so that is a total of 6 times 3, 18. Okay, so we have a total of 18 electrons here. And then you end up writing any extra electrons that are available, which there are 2. You see that? Because of the ion, okay, the polyatomic ion. Now if it was positive, you would subtract 1, but because this is 2 negative, you're going to add 2 electrons to it. Okay, so the 2 negative, so which means plus 2 electrons. So here you have a total of 24 electrons. This is also called electronic bookkeeping, okay, in some ways, because you're trying to go systematically. Are we good so far? Okay, all we've done is just counted the total number of electrons we have in this structure. What do I put in the middle? That's the same rules. Carbon or oxygen? Carbon, okay, the same philosophy. So put carbon in the middle and put the 3 oxygens around it. The first thing you do is you bond singly first, because at least you know that there is at least one single bond, okay, between them. How many electrons did we take care of? 6. So subtract 6 from here. Okay, so then we have 18 electrons. So that was the 3 bonds that we took care of. All right. So we still have 18 electrons to work with, which is really quite a lot. Okay? All right. Is carbon happy here, by the way?
No.
No. Carbon can have up to how many bonds? 4. So you want to make sure that at least carbon has 4 bonds. Okay, in here. The way you can make the 4th bond is by making 1
Double bond.
double bond. Okay, and so you take any oxygen because they're all the same. You take whichever oxygen you want and you make it a double bond. How many electrons?
16.
2 electrons now. So subtract 2 more, and so now you have 16 electrons left. 4th bond on carbon. Okay, so now we have 16 electrons to work with. Do we have any electrons left on carbon?
No.
No, nothing. Okay, we've taken care of this. Now here's one thing, okay, that is for sure, that these 2 oxygens look alike and this one looks a little different, right? Okay, so how many electrons does oxygen have here? 4. And how many of them belong to oxygen? 2 belong to oxygen. So how many remaining for oxygen? 4. 4 remaining. Okay, so you go ahead and put those 4 on that oxygen because that's looking a little different. So we'll finish with that first. Okay, so then minus 4 electrons, and this is for the 2 lone pairs of electrons. So that gives us now 12 electrons. How are we doing? Oh my God, you're thinking like if I wanted to be accountant, I would be in a different class. Okay, now the 12 electrons that we have left over, we have 2 similar looking oxygens. Now what you do is you divide this by 2. You have 6 electrons, distribute the electrons on each of the oxygens. Okay, so which means each of the oxygen now has 6 electrons, which is then 1, 2, 3, 1, 2, 3. And then because it's a polyatomic ion, you put square brackets around it and put 2 minus outside. And I made it seem long. It really is not long. Okay, because I was taking it step by step for the first time. It seems long, but essentially it's not long. Okay, because here's what you do when you're really good at this. Okay, because you say, okay, I got carbonate ion over here, so I have to have at least this much, right, in there. Carbon has to have 4 bonds, so I'm going to go ahead and do this much, okay, at least. And then I have 2 lone pairs of electrons left over here, okay. I have 2 extra electrons, right? I have 2 extra electrons. Technically, all of these oxygens have 6 electrons, correct? Yes, technically all of them have 6 electrons, so which means that this one here now has 8. This one is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Are we good? Very symmetrical distribution of electrons, okay? And then you're like, I got 2 more electrons to fill. Where do I put them? Okay. I'll do that over here. So long you don't violate any of the octet rules, you're fine. Okay? Oxygen should not have more than 8 electrons, okay, in there. Until then, you're quite okay. Good? It takes practice, okay? Not to worry about it too much. You don't have to master everything today, all right? But at least now you have a little bit of an idea how to approach it. So here's what we're going to do for the next 20 minutes.